Okay. Is this started? Yeah. Okay. So a lot of people have was complaining that you cannot understand the notes by yourself. So I'm going to record my explanations, helping you to go over the notes. So I will have to redo the notes I posted on Wednesday. So first of all, I give you an example about a sparse matrix. So what is a sparse matrix? Sparse matrix use the idea that a sparse matrix basically means if you have a matrix that has a lot of zeros, and this kind of a matrix arises from solving, for example, differential equations. So here, the example we're looking at, we're solving this differential equations. Uxx equals f when x is inside of a domain from a to b, and we have two boundary values. When the function u at the point a, so the left point equals a given value, and the function at the right point equals a given value. Then if we discretize this domain a to b into n plus 2 points, so the boundary point is x0 and xn plus 1, and then we have interior points from here. Okay, then we can approximate the second derivative uxx using a finite difference approximation. So for example, we are approximation the derivative at I. So we may use its next neighbor ui minus 1 minus 2 times ui plus 1 divided by 1 over divided by h squared. So this h is the width of your grid spacing. So we'll talk about more later in this course, in this semester, about finite difference and how we derive this difference formula. So the basic idea is instead of solving these differential equations, we're solving these difference equations, and we're having so for each node we have unknown. So this is my solutions from u0, the u function value at x0, u function value at 1, and all the way up to n plus 1. Okay, so this differential equation becomes this difference equation. So if we write this difference equation in terms of matrix form, then the matrix here would be -2 on the diagonal and the 1 on the diagonal that is above the main diagonal, and all the ones that is one below the main diagonal here. So here is my matrix A, and then this differential equation we can write it as here something like a oops AU equals F. Okay. All right, so here A is this matrix, and the U is all the unknowns, U0 all the way up to UN plus 1, and then my F is my function value, and this given nodes. Okay, so it's okay you don't follow the details about this equation here. Let me get rid of this. So it's okay you don't quite follow how we get this finite difference equation. The idea is I'm using this example to show you from applications we end up with a matrix that is only non-zeros on this tridiagonal. We call this tridiagonal matrix because it's only non-zero on these three diagonals, right? The main diagonal, and the one above the main diagonal, and the one below the main diagonal, and all the other place we have zero entries. Okay, so everywhere else is 0. And this is called a tridiagonal matrix here. Okay. And another example is for solving the beam equation. So this we have mathematical model that describes the physics of the beam. So if you bend it, you apply some force to some beam structure, and the internal force is the bending effect is given by this EI multiply the force derivative of the displacement of the beam and equals this force. Okay, so if you again use finite difference approximation for this y, and this is a finite difference approximation formula for approximating the fourth derivative, then if we write it into the matrix form, we got a pentadiagonal matrix. So here is a pentadiagonal matrix. So maybe I should use red. This pentadiagonal matrix here, and again we have only non-zeros on those 5 diagonals, and everywhere else is 0. Okay. Okay, so if you look at it here, we only have so we have 5 non-zeros on each column. So if we ignore the first 2 rows, but for most of them we have 5 non-zeros on each row. So here, 5 non-zeros on each row, and we have n rows, therefore we have 5n non-zeros in this matrix. Okay. Okay. So the idea of those 2 examples is to show you that in mathematics, in numerical methods, we will encounter a lot of matrix that has a very little non-zero entries, and the majority of them is 0. Okay, so we may store them using something called a sparse matrix. So we only need to store the non-zero entries and ignore their locations, and ignore about the 0 things. Okay, so this can be very efficient for computer memories. So for example, if my n is 10 to the 6 power here, then so for this matrix we only have 3n non-zeros, therefore we have 3 times 10 to the 6 power non-zeros. However, if we store the whole matrix, if we store everything including the zeros, we will end up to have to store n square numbers, right? N square entries, which in this case is 10 to the 12th entries. So we can compare how much we have saved in computer memories. So if you're using sparse matrix that only store the non-zero entries, we need only to store 3 times 10 to the 6 numbers. However, if you store everything including the zeros, we need to store 10 to the 12th entries. Okay, so this is just a background information that we will be using for later part of this chapter. Okay, now we're going to talk about chapter 2.5. It's about the iterative method. Okay, so this part can be found from your textbook 2.5. And the idea is we're still interested in solving this problem, ax equals b. Okay, so a linear system equations. So far we've learned a Gauss elimination method and its variations, like Gauss elimination with p-value method, or we can rewrite it as LU factorization, or LU factorization with permutation, right? PA equals LU factorization. But those kind of we've showed you how to calculate the complexity, right? It's the complexity cost is on the order of n cubed, so you need to do n cubed number of times calculations to solve ax equals b if the matrix dimension is n, by using Gauss elimination method, so which is very expensive. And in this chapter we're going to show you another type of method that can be more efficient. So instead of getting the exact solution, we're going to get some approximate solution to this equation using iterative method. Okay, so this iterative method, we've already seen many iterative methods, right? So like in root finding problem, we use fixed point iteration, right? Newton's iterations, those are all iterative methods. So you provide an initial guess, you plug in some updating formula, and the updating formula gives a new prediction, and then you plug back in a new prediction into your formula, get a new one. Okay. Okay, so here's the definition about a sparse matrix. So we say if A that has entries Aij is called a sparse matrix, is sparse if most entries are 0. Okay, so we've showed you examples of solving partial differential equations using finite difference methods. You will end up with sparse matrix, and the storage, you will save a lot of storage by using sparse matrix. Okay, so in MATLAB, if you use a MATLAB type sparse, we'll store a matrix in sparse form. So for example, we can open the MATLAB here. How do we create a sparse matrix? So we can say A equals sparse 5 by 5. So we're creating now 5 by 5 sparse matrix. So if you look at here, what is A? It's nothing. It's all zero. Sparse matrix just tells you about the size, and there's no entry in there. If you want to specify something, let's say if we want to say the first row, first column of this matrix equals 5. Okay, we can do that. And then we can say, okay, the third row and the fourth column of this matrix equals 4. We get that. So now if you type A, it will tell you what A looks like. So instead of printing out the full matrix, it prints out those three numbers, right? 1, 1, 5, 3, 4, 4. So what does that mean? That means the first row, this is a row index, this is column index, this is value. So basically it says A11 is 5, A34 is 5. If you want to look at the full value into the full matrix form, you can use the command full. So you full A and hit enter, and you will see the full matrix, right? So by storing it into sparse form, we only need to store its location and a value, right? The index and the value, we don't have to store all those zero terms. Okay, so this full A tells you that we have 5 on the first row, first column, and 4, the value 4 on the third row and the fourth column, something like that. Okay, so we can also create a matrix by specifying this ijk. So I is like the row index. So let's say we want from 1 to 4th row, and we also want to specify 1 to 4th column. Okay, and their value is let's say 4. So we have, so if I is from 1 to 4, j is from 1 to 4. So we're basically specifying the diagonals. And so here we can say 4, 5, 6, 7 is my value, right? And then I can create another matrix B. It's called a sparse. It has I index, j index, and the value. Okay, so what we did here is, so the I column specifies the I index, the j column specifies the j index, and the C column, the C vector specifies the value of this matrix. So my B matrix is a sparse matrix that has non-zero terms on these positions, right? So if we look at the full B, we can see it's a diagonal matrix with all the diagonals that is specified to be by the C vector 4, 5, 6, 7. Okay. So here for for very large matrix, Gaussian elimination is too costly. So we recall that the standard Gaussian elimination, we need the storage of n square doubles, right? So if we store everything, and for the factorization, the cost of flops is 2/3 n cubed. We need to do this many operations. So if we're solving for a large system, say my n, the dimension of the matrix is 10 to the 6. The storage we need is 8 times 6 times 6 bytes. So we need 8 bytes to store a number. Byte is it's just the memory you use to store a number. So we need to store this many numbers, and that's translated to something you can understand is 8 times 10 to the 6 megabytes, or we can say that it's 8,000 gigabytes, right? So if you are solving a matrix of this size using Gaussian elimination, you better have 8,000 gigabytes of memory on your computer. So normally we don't have that on our household computer, right? So we might have that on a supercomputer, but not for your laptop. Okay, so to work around, so we're going to tell you a more efficient method. It's called the iterative method. So we are going to start with some traditional or the classical iterative method that is designed to use minimal storage computer memory. So the first method is called the Jacobi method. So for example, if we want to solve this system of linear equations, 5u plus v minus w equals 7, u minus 4v plus 2w equals 5, and here. Then if we write it into matrix form, it's like that. So this is my matrix A, and this is my right hand side. We're going to solve as ax equals b. So if we solve it by some iterations, iterative method, right? So we let my xk denote my approximate solution at iteration step k. Okay, so k is the iteration number. So if given the initial guess x0, so we use x0 as my initial guess, the Jacobi method says that we're going to compute my my new guess k plus 1 step from my k step. And how do we do that? We are going to assume the values, the unknowns on the diagonal entries to be my new guess, and everywhere else is from my older guess. So this way, if we solve for k plus 1 steps, if we solve for that, writing everything at the k plus 1 step on the left hand side and all the other things on the right hand side, we'll end up with uk plus 1, vk plus 1, wk plus 1 equals this matrix, and this is my solution or approximation at the k step plus some constant vector, right? So if we write it in a matrix form, this is my solution at the k plus 1 step, multiply matrix B times my solution at the k step or the older step plus some number. So if you're familiar, this is a fixed point iteration, right? So x equals gx, right? So this is my gx function, fixed point function, but for a vector valued function here. Okay, so this is my fixed point iteration. If we have started with a initial guess x0, then you plug that x0 into this formula, you get x1, and then again you plug x1 in here, you get x2, and plug x2 here, you get x3, and so forth. Okay, so for example, if we start with the initial guess x0 with all zeros, and then using this formula, this updating formula for this particular example here, this formula here. Okay, then we get x1 is this vector, and x2 is from bx1 plus d, and for this particular example we get this value, and then if we do it 3 times we get this one, etc. If we do it 10 times iteration, we get this vector. Okay, and the exact solution of that problem is this one, so you can compare. It's accurate, right? So if we only did 10 iterations, and the approximate solution is very close to the exact solution. Okay, so therefore we can see from this example that my xk, the k-step approximation, converges to the exact solution, which is A inverse multiply B, right? So if you want to solve that exactly, we need to do this. Okay. So here's a note I want to say about the iterative method is that, so if you plug in x0 into your updating formula, bx0 plus d equals x1, and you plug in x2 equals bx1 plus d, and we know that x1 was getting from bx0, therefore we replace x1 with its updating formula bx0 plus d and expanding everything, so we got the b squared x0 plus bd plus d. And for the third iteration, okay, so we can do this again, and we know that x2 is this formula here, and plugging x2 with that formula and expand, we get this term. Okay, so keep on doing that for b4, we get this, and we can get the common factor d out, so this becomes b cubed, b squared plus b plus I is identity matrix, and for the n step, we can say that bxn x0 plus I plus b plus b squared all the way up to bn minus 1 d. Okay, so this way this goes, we will show that this one will go to 0. And the other thing approximate I minus b inverse. Okay, so this is analogous to this formula, this Euler theory, the Taylor theory of 1 minus x to the negative 1, which equals 1 plus x squared plus all the way up to x and infinity. Okay, so this way, in the limit form, if xk goes to infinity, my xk will go to x, the exact solution of this guy. And we can rewrite this into I minus bx, right? We move this term to this side, okay? And getting this x out, so we will get this equation. Okay. Okay. And that's why we say this, because the exact solution of this one would be x equals I minus b. Oops. Trying to create I minus b let's do that. Okay, so this one, the exact solution is x equals I minus b. So how do I? Inverse multiply d. So that's why we say this one is approximation of I minus b inverse, and this one goes to 0. Okay. So if we write the Jacobi metric, Jacobi iteration method in terms of a matrix form of a Jacobi, so we're going to solve this matrix x equals b, and my A is a matrix Aij. Okay, so now we're going to decompose it into 3 parts. So L, D, U. So here this LU is not the LU in the LU factorization. So here's, I need to point this out. This is not, okay, not the LU factorization. Okay. Okay, so what? So if it's not the LU factorization, what is this L and U? Okay, so this L okay, so this L is basically the lower part of your matrix A. So everything underneath, below the diagonal is my L. Okay, and the D is my diagonal, and the U is my the entries that is above the diagonal. Therefore, we can just rewrite A equals its lower part plus its diagonal part plus its upper diagonal part. Okay, yeah. Okay, so then my AX equals B can be written as because A equals can be written as the lower part. We're going to still using the old solution, and the diagonal part we're going to use the new solution, and the upper part we're going to use the old solution. Therefore, we're writing AX equals B. AX equals B in terms of this iterative method, and we reorganize terms by solve this guy. We get my new vector xk plus 1 equals negative d inverse L plus U xk plus d inverse Okay, and if we call the whole thing a matrix B, and this becomes x k plus 1 equals bx plus d. Okay, so this is same form as before. And my D inverse, since D is only the diagonal entries, right? So its inverse matrix is very easy to compute. It's just the reciprocal of all the diagonal entries. So if it's A11, A22, AN on the diagonal, and the inverse would be 1 over A11, 1 over A22, and 1 over AN. So note that if we want to use Jacobi matrix to work, all my diagonal entries has to be non-zero. Okay, otherwise this is not working. Okay, so component form of the Jacobi matrix. Okay, so if we write it into component form, writing instead of a matrix form, so this one for ith equation, we're going to have my ith row multiply all the unknowns, adding them up equals bi, and we're going to taking out the diagonal parts and using the new approximation here only for the diagonal parts. Okay, aii is the diagonal part, and all the other parts, say j not equals I, is using the older solution, so we can write it this way. And if we solve for xi plus 1 xi as a new solution, so we end up with the same thing here, but just in terms of every entry, right? So this is very useful if we're using sparse matrix, because here we know that what we need. So when we know the I index, j index, and the value, so we can very easily specify the in using sparse matrix. So for example, if we are solving equations like that, we have 2 on the diagonal, -1 on the top, and the -1 on the diagonal below the main diagonal. So this problem was from the boundary value problem we see at this example here. Okay, just give you some value. Let's go here. Okay, so if we define x0 as 0 and xn plus 1, so this is my solution. So, oh, sorry, here should be xn plus 1. We're missing one. Why the n plus, why it's keep correcting me? It just made me write. Anyway. So here we need x n plus 1. Okay. Here. Okay, so if we said x1 equals x0 equals, oh, here we're also missing x0. So if we're saying x0 equals 0, xn plus 1 equals 0, we're getting, because they are equals 0, we can, does not need to include them in my equation, okay? Just ignore what I said. So let's say we have this equation we want to solve, and if we write it into the components form, right, write it for each component, and this one becomes negative xi plus 1 plus 2xi minus xi plus 1 equals bi, and for all my equations goes from 1 to n. And the Jacobi iteration says if we're using the new approximation for my diagonal parts and the old approximation for the other parts, then we can write it in this way. And if we solve for xi plus 1, we end up with this equation, right? So here we can see that we only have, we only need, when we're solving for xi, we only need its left neighbor and the right neighbor. Therefore, we only have, if we're using sparse matrix, we only, my matrix B here would have only 2 diagonal parts, okay? So this is an efficient way to implement the Jacobi for this example. And Jacobi may not converge for all the matrices, but the Jacobi does. And in next lecture, I will tell you under what circumstance Jacobi iteration will converge. But Jacobi does converge for an important class of matrix. It's called the SDD matrix. So what is a SDD matrix? Here I just give you the definition. The SDD matrix is called the strictly diagonally dominant matrix. So what's that? What does that mean? It means if we have an n by n matrix A, okay, so if all the diagonal entries is strictly greater than the sum of diagonal entries on row I, then this is called the strictly diagonally dominant matrix. And for this type of matrix, my Jacobian iteration matrix will converge. Okay, so I think I can stop here.